Now let's talk about energy and momentum in special relativity. I'm not going to try to derive E equals mc squared, or any of that. The attitude is just I'm telling you the theory of special relativity in the most convenient way of looking at it for this course. So I'm just going to present results, basically, and show you how to use them. So we already introduced the idea of a tangent vector to a curve. And I may have actually neglected to use the terminology world line. World line x mu of lambda. It's another name for a curve. Usually only when it's time-like you call it a world line, but because it's like your line through the world, I guess. Time-like world lines represent observers. Anyway, it's just a parametrized curve. We already talked about this. And we talked about how a world line defines a tangent vector. T mu equals dx mu d lambda. And all that rigmarole with basis elements and transforming, that's in the past. We did that in order to establish the rules of the notation for dealing with components of good vectors, where the equations take the same form in every Lorentz frame. And so this is a good vector, tangent vector, dx mu d lambda. Notice the overall scaling is arbitrary. So if you consider a new parameter, lambda prime, so lambda prime is some function of lambda, what happens? Well, we just have the chain rule. So dx mu d lambda prime is dx mu d lambda prime. And so this is the old tangent vector, right? This is what we called t mu. And this is just some function of parameter, lambda prime or lambda. Okay, so you think of the curve as something like this, but you could have two different tangent vectors, which we'll draw loosely as two arrows of different lengths. So it could be that one, or since I called it prime, it's a little, I don't want to confuse you with, it's one coordinate system, two different parameters. So maybe instead of lambda prime, I'll just call it sigma. Sorry to make you erase if you're copying down, but that'll be better in the long run. So dx mu d sigma is equal to dx mu d lambda d sigma. So this is some function of sigma or lambda. It doesn't really matter. It's a function on the curve. So you can rescale the tangent vector freely at every point on the curve. So we might call this one might be t mu, I don't know what a good notation is, with respect to lambda. And some other one might be this one that's in the same direction in the tangent space at the point, but we draw as longer because its components are rescaled. So this might be t mu sigma. Okay, so the length of, I shouldn't really say length because I haven't put the metric in, but colloquially we often say the length of the vector is arbitrary. Tangent vector could be anything. Okay. Now, we always want our notions to be invariant under the freedom in our formalism, right? So we talked about Lorentz transformations a lot. We wanted our, tensor laws to take the same form in every Lorentz frame so that we don't build in preferred Lorentz frames. Similarly, we don't want to build in any preferred notion of a tangent of a parameter in this case, right? So everything physical that we compute, we want to be independent of the parameter. So let's check a couple things. So first of all, a world line definition is called, and there's three cases. So it's called time-like if now we have a metric, eta mu nu, t mu, t nu is negative, just the natural generalization of the space-time interval. Null if this thing is 0. and space-like if this thing is positive. Okay? So is this independent of the parameter? Any ideas? Yeah.
Yes, we rescue the question.
Anyone have an argument that it's independent of the parameter?
I think yes. My logic being, well, partly being space-time, and these are the same terminologies we used about the
Yeah,
space-time.
okay.
Well, that thing's invariant. But,
No, that thing's invariant under Lorentz transformations. Here, we're talking about a reparameterization of the curve. It's a different invariance.
okay.
Did you have a comment, Peter?
Yeah, I think it is because if you were to apply this chain rule,
Yeah.
on the left side you'll get something with like multiplied derivatives of the new parameter, but that doesn't matter because those are always just multiplied by something and there's 0 on the other side. You can always just divide them out.
You're going to get 2 factors of the thing.
There you go.
Because it's going to be squared.
That's right. So
you could have it like on the same axis but anti-parallel, and therefore have a negative sign and change your sign on this, but the fact that it's squared.
right, exactly.
Resets it
So
back.
if you had a minus sign, we would call that like a flip of time orientation, like you just change, if it's a time-like world line. But it's still, this definition is invariant. Okay, good. So teamwork, we got there, right? So t goes to t times f of lambda. Well, then eta mu nu, t mu, t nu goes to eta mu nu, t mu, t nu f of lambda squared. But this thing is, whoa, that doesn't look like a squared. Squared. But this thing is positive. Okay? So it's independent of parameter. Good.
Is there ever a case where you have some like complex parameter and your squared thing is...
Complex numbers?
Yeah.
No.
No? Okay.
We don't need any complex numbers at all to do general relativity.
Yeah, that's what I was hoping for.
Oh, come on. Complex numbers are awesome. Okay. All right. Good. So that's a good definition. Another one we gave before was time elapsed. Time elapsed on a clock moving on a time-like curve, world line. So that's messier, but I think it's worth the speed gain. So we had a formula for that. It said tau was the integral of the square root of, let's write it more nicely. Remember, it was dt d lambda squared minus dx d lambda squared minus dy d lambda squared minus dz d lambda squared. So we can write that as minus eta mu nu dx mu d lambda dx nu d lambda d lambda. Okay, so is this one independent of parameter? And if so, why? Yep.
I've got like a messy physics canceling derivatives answer.
Yeah, that's basically it. So
Okay, yeah, you're-
we see that now we have to use in more detail the functional form. We can't just use that it's the function of lambda. Well, we can. Doesn't really matter. If you change lambda to something else, so if you go to sigma of lambda, then d lambda would just be d lambda d sigma d sigma. So you would plug that in here, and then it's the opposite chain rule here, and the d lambda d sigma will cancel out. Okay, so this is invariant, also independent of parameter. Good. I mean, this would be a disaster if it weren't, right? Because this is supposed to be directly measurable. This is supposed to be wristwatch time on that curve. So if it depended on how you parameterize the curve, you'd have to retract your paper claiming it was the formula for wristwatch time, without even having experiments done. Like, it just wouldn't make sense. Okay. Now, one of the things that's often very confusing, but I assign that homework problem with the hyperbolic trajectory to try to give you some practice doing it before it's introduced in class, is using tau as a parameter. It sort of looks strange because we think of computing tau from some other parameter, right? But think about what we need. If we kind of just look at a little, it's easier to do it without the integral signs. If we just write this thing as d tau equals square root of minus eta mu nu dx mu d lambda dx nu d lambda d lambda, you know, what do we have to do to use tau as a parameter? Well, suppose lambda equals tau. So then what do? Well, we have d tau here, and we just have minus eta mu nu dx mu d tau dx nu d tau. But you see that for these two things to be equal, because we have a d tau on each side, this must be 1. Okay, so if you use tau as a parameter, which you've already done on that homework problem, so hopefully it doesn't seem so mysterious, then it follows that eta mu nu dx mu d tau dx nu d tau equals minus 1, right? Because of that minus sign in there. To get the thing in the square root to be plus 1, I need a minus sign. So this is an important equation, and when we use tau, we give the tangent vector a name. Okay? So we call it u mu equals dx mu d tau. This is called the 4 velocity, so I'll put 3 equals to show it's a definition. Because it's sort of it's a nice generalization of 3 velocity. We'll explore it some more. But the one way to think about the definition is this formula here. So this u mu satisfies eta mu nu u mu u nu equals minus 1. And you use this equation a lot in homework problems. Often this is a much easier way to get to parameterize by proper time than going through the whole rigmarole you did on the homework. Yeah. Well, the formula for the time elapsed over a small interval I'm writing as d tau. You can think of it as integral over a little bit. And then the right-hand side would have integral of this. That was our definition of wristwatch time. And what I've done is I've set lambda equals tau. I've said, suppose I want to use the same parameter, the proper time as the parameter. So this d lambda just becomes d tau, and in here, instead of dx d lambda, just have dx d tau. So now I have an equation that says d tau equals something times d tau. So the something has to be 1. That's all there is to it. Okay. So this is our 4 velocity, and notice it's just a normalized tangent vector. So a time-like world line could have any tangent vector t mu. This is a special choice where we set it to minus 1. Remember, it had to be negative, and we proved that the sign of it was invariant under reparameterization. So for a time-like world line, we can't make the tangent vector's length positive, but we can set it to a canonical negative number, and we choose minus 1. And that has the interpretation that our parameter is proper time. Okay? And we're going to do this in curved spacetime too, which is why I go so slowly. Because I'm not going to go that slow when we get to it again. Any questions? Uh-huh.
With curved space, obviously eta becomes g, but are the u's always the same? Even in curved space, you just say it's...
Same formula, yeah, will be. And the eta mu nu will become a curved metric. Yep. So that's the for velocity. And then we also introduced the for momentum. So the for momentum is defined as p mu equals m, mass of the particle. So sometimes this is called rest mass. We're not going to say rest mass because that kind of implies there's some other kind of mass. And in older books, they talk about like a relativistic mass. It's not standard anymore. So we just say this is the mass. And it gets multiplied by the for velocity. Okay, and this is a natural thing to do. So our for velocity was dimensionless. And now we've multiplied by a mass. And we have the speed of light set equal to 1. So mass is like energy and momentum. So we have the for momentum. And what is the interpretation of this thing? So P upper 0 is the energy of the particle in some frame. So it's frame dependent, right? Some frame x mu equals, t xi. So some frame, if you get the components of this vector, the 0 component is the energy. And the spatial components are the momentum. Particle in some frame. Okay, so the equation with mu holds in any frame, but that just relates p to u mu. And the interpretation in your favorite Lorentz frame is that the time component is the energy and the space components are the momentum.
That is true for any frame?
Any Lorentz frame, yep. Right, we're not deriving this, just stating it. So now is where we really get some physical content to this mathematical framework. So far, really the only physical thing we talked about was wristwatch time, right? So now we talk about, what energy your particle detector would register in your Lorentz frame if you were studying, collisions. Okay. So these things transform like 4 vectors. That's one of the neat things about relativity, that energy and momentum get sandwiched together into a 4 vector. And we can use that to determine some useful formulas. So first of all, let's do a frame where the particle is at rest. So in this frame, of course, x equals what? Well, they don't have to equal, but x, y, and z are all constant. Right? That's the definition of rest. So in particular, dx d tau equals dy, d tau equals dz, d tau equals 0. So in that frame, where there's a particle at rest, we would write u mu equals, well, let's just leave this part the same. U mu by definition is dx mu d tau. So the time component is just dt d tau. And now the space components are all 0. In this frame. Okay, I'll just remind you that that was the definition of u mu. It was dx mu d tau. So all I've done is write that out and set the spatial components to 0 because it's not moving in this frame. But this is going to get us somewhere because remember that useful defining condition, or equivalent condition for saying we've used tau is that eta mu nu u mu u nu is -1. So let's use that. So minus 1 is a to mu nu, u mu, u nu. And now the nice thing is u here only has a 0 component. So this is the same as a to 0, 0, u0, u0. All those other terms with spatial coordinates are not there because ui is 0. And so u0, 0 is minus 1. u0 is dt d tau, so this is minus dt d tau squared. And so the minus cancels, and we learn from this simply that dt d tau. Now it could be plus or minus 1, right? But we want to pick the plus so that the particle is moving into the future. T increases as tau increases, so this, this if you like, this doesn't matter much. So we pick it to be plus 1. So that was a long-winded way of deriving that in this frame, the four velocity takes the following form: 1, 0, 0, 0. Okay, so that's our straight line, and our tangent vector u mu is now normalized, points up. Okay, but I claim I've derived E equals mc squared. I mean, not from physics, but from these other definitions, because that means the form momentum, which was defined as the mass times u, is just m 0, 0, 0. And so in this frame, P0 is the energy, so E equals P0 equals m. And maybe just once I'll put c squared back in. Remember, c was 1. So now we have E equals mc squared. Okay, so this is how the form momentum keeps track of energy in the rest frame of a particle. But now we can get a nice equation for a particle, for the same particle in some other frame where it's now moving with constant velocity. So let's boost. So particle is moving with the constant velocity. And here the notation is very nice. So we just say our new constant velocity, our frame that's moving with a relative velocity v, we'll write p mu prime is p mu lambda mu prime mu. And so if we remember lambdas, this is going to come out to p0. How does the lambda work? So lambda, so there'll be a 0, there'll be a, so, oh, I need to choose me. That's what's confusing me. Let's do it out. Oh. So let's do one coordinate at a time. So let's do p0 prime. So that'll be p0 gamma 0 prime 0 plus p, and let's boost in the x direction. So px gamma 0 prime x. Now p0 was m. So this is the old frame. So that'll be m. And let's look at gamma 0 prime 0. That's gamma. It's just gamma? It's just gamma, right, because t prime equals t gamma t minus vx. Good, so it's just gamma, and then x prime is gamma x minus vt. So, but px is 0. So we have p0 as m gamma, and we do the same thing for pi prime, or let's just do x. Px prime is now, we still have to do p0 gamma 0 x prime now. Gamma x prime 0 plus px gamma x prime x. And now p0 was again m. Gamma x prime 0 is just gamma. Lambda. I'm saying gamma for these big ones. These are lambdas.
Minus gamma v.
Yep, that's right. I wrote x first here instead of t. Thank you.
And you just the minus direction to get a positive direction.
Okay, well, we'll figure that out when we're done. And then px was also 0. And so this is minus m gamma v. Okay, so now we can come here and notice that p mu prime, there's a common factor of m gamma. And I got 1 minus v. So the particle is moving now with constant velocity minus v in the x direction because I boosted with velocity v in the x direction. So, I mean, yeah, maybe I should just flip the signs. So let's give it constant velocity plus v in the x direction. So the boost is minus v. So I have to change this up here to a plus, this up here to a plus, and then this will become a plus. And then this will be a plus. And so this is a nice formula to remember. Okay, so in an arbitrary frame where a particle is moving with some constant speed, so if particle has velocity v, then we would say, you know, its energy, which is now called E prime, is m gamma. So it's not just E equals mc squared. There's a gamma there. And its momentum, can now make this v in any direction if we like. Its momentum now is m gamma v. Okay, so we got that just from the Lorentz transformation. One thing I realized I didn't say when I introduced the 4 momentum is the normalization condition. That's going to be important. So I'll put it back up here and then write it out again. So remember, u had norm minus 1. So p is going to have norm minus m squared. So it's going to be p, so eta mu nu, p mu, p nu is minus m squared. Okay. One thing that's nice to see about this formula is, like, as a sanity check, let's make sure this like reproduces what we know about energies of moving particles from, you know, freshman physics. So let's consider slow motion. So what's slow? Well, it means v is small compared to the speed of light, small compared to 1. So gamma, remember, was 1 over the square root of 1 minus v squared. And then when we Taylor expand this, and we can write this as 1 minus v squared to the minus 1/2. And then we can approximate that as 1 plus minus v squared. 1, we'll bring down minus 1/2 plus minus 1/2 times minus v squared plus higher order terms. And that's 1 plus 1/2 v squared And so if we go here in our slow motion limit, E of the moving particle is m plus 1/2 mv squared. Okay, so there's our kinetic energy. I should make approximate here. So we call this kinetic energy. And this we call the rest mass energy, or rest energy, maybe. Okay, so if it were not moving at all, we'd have E equals mc squared. And when it is moving with small velocity, we add the usual kinetic energy. Any questions? Yep.
Once we get going, once we start getting to high values of V relative to 1, so like we got to
Yeah.
like half or something.
Sure.
Why is it that we ignore this kinetic energy part? We just go back to using m gamma.
Go back to using what?
Like we just go straight back to m gamma instead of like caring about the kinetic energy
Oh,
at all.
you can. You could define the kinetic energy as m gamma minus m if you want to just subtract off the rest mass energy. But it's just not as useful a concept. It's easier to write m gamma. And we'll see in curved space-time, energy is even more subtle, actually. We have to think, gravitational potential energy will make an appearance buried in that formula. Okay, what else? We need to do the famous relativistic energy momentum equation. Let's do that from the normalization condition. So the normalization of P mu, recall I wrote just a minute ago, was P mu P nu, with eta mu nu had to be minus m squared. So let's write this out in any Lorentz frame. So the left-hand side is minus P0 squared plus P squared. And the right-hand side is minus m squared. But remember, P0 was just energy. So we can write this as, so P0 is just energy. We can write this as, I don't know how it's normally written. Maybe we multiply E squared minus P squared equals m squared.
Minus p squared to the right first. Take the square root.
Sorry, I'm having technical difficulties. Yeah, what's the famous way of writing it? M squared equals or E squared equals? It's probably E.
Yeah, E is the E squared equals P squared plus M squared.
Yeah, that's probably how people write it. E squared equals P squared plus M squared in any Lorentz frame. So if you studied special relativity in the context of like particle physics, this is an equation that's emphasized. It's the same as the normalization condition. Okay, the last thing I want to do is null vectors a little bit. So this was all for time-like world lines. Yep.
So we wrote before the E as a component of P.
P0, yeah, in some frame.
So
It's frame dependent.
so now P0 will depend on the other three components of P.
I mean, there's an equation obeyed by the four components, yes.
Oh.
So if I give you, I mean, that's what this equation says, right? If I give you the momentum and the rest mass, you know the energy. All right, so now let's do null world lines. So null world lines are for massless particles, like light. Or maybe neutrinos, although they have a small mass. But it might be a good approximation in some circumstances. And you can also have a purely classical statement. We're really not quantizing anything, so I shouldn't really talk about a massless particle. But you can look at the ray optics limit of Maxwell's equation and make precise what's meant by a null world line. It's the ray is null in space-time. But we'll just think of them as things moving at the speed of light. So now, remember, eta mu nu, t mu, t nu is 0. So there's no preferred normalization, right? When eta mu nu, t nu was negative for a time-like particle, we could set it to -1. And that was really nice because it got us to, representing the relativistic energy momentum relation in a nice way as a simple normalization condition and so on. But there's no analog of tau. There just isn't, okay? We can't normalize. You can't normalize t because it's 0. That says normalize, I promise. Now, you still often, when you deal with light, want to use a parameter, but you can't think of it as a normalization condition. You want to use a preferred parameter. And so instead, we often just pick lambda such that we have the same interpretation. Okay, so now we're going to call it, well, let's write it this way, such that T0 is energy. So, now you probably need h bars to relate that to frequency in a classical solution. Ti equals momentum. And when you do this, we call it p mu again. Okay? So this t mu is p mu. Okay, so we can write, p mu equals dx mu d lambda. And we can say now p mu p nu equals 0. But there's no way to find lambda by imposing this normalization condition in the same way there was with tau. This normalization condition isn't really a condition. It's part of the definition of a null world line that this is true. So this will be true with any parameterization. But we just pick lambda, according to the physics of the problems, so that dx mu d lambda is p mu, usually. We won't do too much with null world, a little bit. Mostly we'll be talking about time-like, but this is an important caveat. So you don't go around in circles looking for the analogous special normalization condition. This normalization condition does not exist. Any questions? Just as a comment, we can also introduce a notion of force. The homework problem on doing this with the Lorentz force. We can do a lot of interesting physics in this class with no forces at all because gravity is not described as a force in general relativity. It's just promoting these equations to curved space-time gives you gravity. But if you have other forces like electromagnetic or anything, the most natural thing is just to define it as, Newton's second law in the space-time. So dp mu d tau. And relating that to the 3 force is something you'll explore on the homework. The extent to which you get relativistic corrections to F equals ma is going to be a homework problem for next week. Any last questions? Yep.
So we talked about a 4 velocity as part of the momentum. Obviously, you're taking a derivative with respect to proper time here. Is that like, I guess you probably don't call it that, but like a 4 acceleration?
Yeah, if it were, as long as the rest mass is constant for your particle, then I can plug in p equals mu. So if m constant, then f mu equals m du mu d tau, and then this would be the 4 acceleration. You wouldn't use it if it weren't constant. It basically will be always. Yeah? Go ahead.
I was gonna say, like, I know we talked about like the time, like, and the null speeds. Is there any use for like any sort of space-like stuff, or is it just like
Not really.
simple, don't bother?
Yeah, nothing goes that fast, and you never need like a funky parameterization of a string or something. I don't know. Doesn't come up in. Yeah?
So like for that, especially for cores for the zeros component, would have like P0.
Yeah, it's the change in energy. It's the power. The 0 component is the power. Good point. Okay. I'll see you guys all next time.